Okay, so this is part 2. I wanted to say one more thing about the way in which we think about the classical double slit experiment, for instance, with light. So when this is a screen, right? So we have the 2-slit mask, waves arrive, they hit the screen. What we see on the screen is we see a pattern of, they're called fringes. They call them fringes for some reason. I call them spots. They call them fringes. So you see bright, then dark, bright, dark, bright, dark. Let me use a different color so it actually does look like a bright. Right? And we just discussed the reason for that, explained by the wave nature of light. Another way to depict this is to make a plot of intensity versus the vertical position. So let me use this axis. This is the intensity axis. I stands for intensity. Intensity, as we discussed, is energy per area per time. But it turns out that with light, intensity is proportional to the square of the electric field. So it's always positive or 0. And so I'm just going to turn my head, okay? I'm going to make a plot with a head like this. So this will be the axis along the screen, called y. And this axis is the intensity. And so viewed in this way, we can plot intensity as a function of the location on the screen, and it will be the following graph. It turns out to be actually a sine squared for a simple 2-slit experiment. If the word intensity gives you a headache, think brightness. Intensity is basically brightness. Okay, so intensity, brightness. And so what I'm plotting here is I'm plotting brightness as a function of location on the screen. So this is a tool, this is a language that we use to describe the double slit interference, double slit experiment. This is supposed to be a perfectly periodic sine squared function. It's very hard to do that on iPad, but you get my intention. So now we get to the heart of it. How can you understand this behavior in the context of particles? Pause this video and think about this. You have intuition about particles. You've seen this experiment, you've done it. We just told you that a light acts like a particle. How can particles give rise to this kind of a interference pattern? Pause the video, think about it. We will also do this in discussion sessions. A very, very good question. I'm going to continue. So first, let me write down the question. Okay, very good question. Pause the video, think about it. Well, so here's a possible explanation. Could it be that these particles interact with each other in some way as they pass through slits? So it's kind of a dance between particles, interactions. The simplest form of interaction is like bumping into things, but it doesn't have to be bumping, right? It could be some kind of complex form of scattering between many particles that gives rise to this uh, kind of a pattern. So the possible explanation is interactions between the particles. We call them photons. But again, it doesn't have to be photons. We'll discuss that the same story carries over to traditional particles like electrons, neutrons, helium atoms, and so on. So again, ideas are cheap. It is very tempting to just say, oh yeah, I know, and go home. But if you want your idea to have some weight, that is not enough. You better give us also a recipe, a prescription for how to test, how to convince us. And then I will say, aha, let me do this. You think it's because light is particles, fine. I'm going to push it to extreme. I'm going to send one photon at a time. If I send only one photon at a time, you cannot use this as an explanation. It will not be a good cop-out because now you're sending only one particle at a time and it has nothing to interact with. So therefore, if that's the explanation, let me scrutinize it to extreme. And let's think what happens if I send only one photon at a time. Okay, so test. Send and then if photons are particles, as we traditionally think of as particles, what do you think would happen? If you propose that the reason you get interference with particles is because of interactions, I send one particle at a time, I eliminate interactions, well, the interference pattern should disappear. Agree? Pretty logical. Note that the wave theory, pure wave theory, would predict that the interference pattern always survives, no matter how little energy, how small the flux of energy is. With particles, you decrease the flux of energy by decreasing the particle current. Each particle carries some amount of energy. In wave theory, you decrease the flux of energy by dialing down the amplitude, dialing down the intensity. And with wave theory, it doesn't matter how small the intensity is. Wave theory would predict that interference pattern would always be there. It would just get dimmer and dimmer and dimmer. Let me just put that. All right, this is energy flux. Energy flux. So what would happen? Again, I told you we talk of double slit experiment because it's a workhorse for us to really bite our teeth into wave particle duality. But such experiments have been done. And what they found in those actual experiments that have been done, what they found is that what actually happens when photons enter one at a time does not fit either our notion, our classical, our traditional notion of particles, nor does it fit our notion of, nor does it fit our traditional notion of waves. So what actually happens when photons enter one at a time does not fit either picture the way we think of it traditionally. Or I could say it fits neither the prediction that the interference pattern disappears. That's a particle prediction. If you send only one particle at a time, you would predict that the interference pattern disappears. And neither does it fit the purely wave picture that as you lower the energy flux, the interference pattern is always there, it just gets dimmer. Okay. All right. So here we go. So here's what happens. I'm going to bulletize now. I'm going to list what actually happens. So first of all, point number one. If we expose the screen, let's say we put a photographic paper, we can also put CCD device, but photo paper is simpler. It's a simpler thing. It's a more transparent what's going on there. So let's say we put the traditional photographic paper on the screen. So if we expose that paper, if we expose that screen during short amount of time, so that only a few photons had time to arrive, we do see localized impacts and not a very weak fringe pattern. Okay, so if expose the screen during a short enough period of time, so only a few photons arrive, we see localized impacts, not a very weak fringe pattern, like I discussed here in this parentheses. So if I'm facing the screen, I will make two drawings. One is side view, the other is facing the screen. If I'm facing the screen, what I see is I get just localized impacts. Usually the slits, when we think of slits, we think they're narrow and long slits. So the screen is two-dimensional. Look at the screen. If I take that photographic paper and I develop that paper, this is what I would see. So these are localized bright points, and these are localized impacts. Okay, so this is, and here's a side view. So here's my double slit apparatus. Here's my screen, and we get occasional points. Notice that these points occur randomly. Distributed randomly. So this is very important, that there is randomness. And I will make an argument that this randomness is not because our experiment is sloppy. It's much deeper than that. Very important. In any case, we see that this is definitely not a traditional wave picture. If it was a traditional wave, you would have smooth interference pattern. It just gets dimmer and dimmer and dimmer and dimmer and dimmer. Okay, but that's one part of the story. But before I tell you more, I want to pause, I want to step back, and I want to digest. I want to ask you a question. So far, this fits a traditional particle picture. Localized impacts sounds like a particle. So what's the big deal? Well, then, what do you predict will happen if we send more and more particles and the paper, the photographic paper, will accumulate where those impacts occur? What do you expect from the particle picture that so far this suggests? So this is a question to you. I'm sort of stepping up the stage right now. What do you expect of the pattern accumulation of impacts is more photons arrive? So far, everything fits a particle picture. Well, what do particles do? When we think of particles, we think of things that follow trajectories. Okay? So classically, a particle follows a trajectory. You throw a baseball, it follows a ballistic trajectory. You have Earth and a comet. It follows a hyperbolic trajectory, for example, or maybe elliptical trajectory. You have Earth and Moon. This is a comet. This is a baseball. Earth, Moon. It follows elliptical trajectory, but nearly circular. It's actually not a circle, it's an ellipse. So this is parabolic trajectory. This is hyperbolic or elliptical trajectory, right? This is elliptical, nearly circular. So now let's get back to double slit experiment. what do we expect with this trajectory picture in mind? Each photon being like a pebble, like a classical notion of a particle. What do we expect from this classical intuition? Well, here's a double slit. Here's a screen. I've drawn this many times already. Imagine I'm shooting bullets through two slits. Okay, so here's the first bullet, boom, boom, it lands here. Here's the second bullet, boom, it lands here. And let's say some of these bullets, pebbles, particles, maybe they, this is not good. This one I don't like. Maybe it kind of ricocheted off of the edge. Maybe it's not a very good experiment. But if I'm aiming towards here, I'm going to get a lot of impacts right here and occasional stray impacts right here. And if I have two slits, well, I'm going to have the same thing through this one, right? So I'm going to get a lot of particles that hit here and fewer particles that hit here. I'm going to get a lot of impacts that hit here and fewer impacts that hit here. And a good way to depict that is to plot the density of impacts versus the position on the screen, right? So what I could do is I could plot the density of impacts versus the y coordinate. And what I would get is I would get some kind of a double bell curve. Right? So there's a lot of impacts here, fewer here, and then a lot of impacts here and fewer here. Agree? Pause. See if you're in harmony with this. This is very important. And by the way, what would you expect if I covered one of the slits? Well, one of these bell-shaped lobes will disappear. And if I cover one of the slits, you would expect something like this. Okay, so if I cover and I place the screen, then particles would only enter through here, and again, they will accumulate here. And the pattern of accumulation, the density of impacts, will be a single bell-shaped curve. No wiggles, no nothing. That's what this trajectory picture predicts. And one more thing, if I improve my experiment, if I'm very careful, if I make sure that I eliminate experimental randomness, okay, particles don't hit the edges of the slit. I try to make sure that every particle is sent identically with identical conditions. Then the spread will diminish, and I would expect some sharper peaks, right? And better and better and better and sharper and sharper and sharper. Agree? This is very much what we expect from our everyday understanding of what a particle is. This is what we expect from this view of particles, things that follow trajectories. Agree? Okay. So now I'm going to continue telling you the story, what happens. So point number one, I gave you first piece of evidence that when we expose the screen for a short period of time, we get particle-like impacts or impact that support the particle picture. And that's point number one. Now I said, what happens if we keep accumulating these things? Now I will tell you what happens. This is point number two. This was an aside, now point number two. So this was an aside. And now point number two. Okay. As more and more photons arrive, each one arrives, makes a dot on the photographic paper, it's recorded on the paper. The individual random impacts accumulate and begin, I'm gonna like this now, resemble the familiar fringe pattern. Now I'm really throwing you a curveball. That is not expected. And I'm gonna draw again, not the side view, but the face view. So I take out the paper, I look at the paper, here's what I see. Now this is a lot more of these impacts. Again, the slits are narrow slits, narrow and long slits. I'm doing this in real world, not in the two-dimensional world. So a lot of them will accumulate here and very few will fall in what traditionally we think of as the dark fringes. And you would get sort of, you would accumulate this for hours and you would get this kind of a double slit pattern. In a lecture or two, or maybe tomorrow, I will do a simulation where it's much, much prettier and it would be something like that. But I think you're beginning to see with my hand simulation, the pattern emerge. That while these individual impacts are random, and when a few of them fall, we don't see any pattern. But when we allow a lot of this impact to happen, when we allow a lot of the energy to, when a lot of energy has hit the paper, in energy perspective, we do get back this we get back the familiar interference pattern. And let me visualize it again like this. So I can plot, what color did I use? The blue color. So I can plot the density of impacts versus this y-axis. This was density of impacts. And it would be this kind of a familiar thing. Okay. Because it's a random process, you can think of the density of impacts as a proxy for probability where the next particle is going to land. So the density of impacts this is proportional sign. This is a very important observation. I really should do this in red color. Okay, I'm going to continue telling you the story. And so if I wait longer and longer, if I wait long enough to capture a very large number of photons on the screen, we get back the familiar bright and dark fringe pattern. We no longer see individual impact. There are just too many. And we get back the regular bright and dark fringe pattern.